Hello again to another Agricolor React. Today we'll be watching what the polar vortex will do to Earth this decade. And looking at the weather, what's going on with weather all around the world, it's quite scary stuff. So it's from Astrum, it was uploaded only this month, so 3rd July 2023, and you know what guys, let's just get into it, and let's start.
When I started my Milankovitch cycles video with a reference to Game of Thrones, I didn't realize exactly how apt my analogy was. In that TV show, the armies of the Night King in the north are trapped behind a giant wall. Just like in the TV show, it turns out that on Earth there exists a powerful, icy force to the north that is seeking to overthrow its bounds and rush southward. That powerful winter is also kept at bay by a mighty wall, one that allows the nations to the south to enjoy relatively tranquil conditions. And just like in the TV show, that wall eventually gets breached in a wave of ice that sweeps down and threatens the lives of all those in its way. You might not recognize what I'm talking about. Where is this wall? And what is the icy winter it protects us from? The answer to the first question is a name that I find particularly cool: the Polar Night Jet.
Huh.
And it turns out that the polar vortex it protects us from is a biting chill not to be underestimated. What is the polar vortex, and how does the Polar Night Jet protect us from it? I'm Alex McColgan and you're watching Astrum, and today we'll learn more about this climate-shattering phenomenon and what happens whenever the Polar Night Jet breaks down and the polar vortex is unleashed. There are actually two polar vortexes, one at each pole of the planet. And even there, each vortex comes in two parts: a tropospheric polar vortex, spinning in the section of the atmosphere known as the troposphere, from ground level up to about 10 to 15 kilometers. This is where 75% of the total mass of the atmosphere resides. Above that lies the stratospheric polar vortex, a technically separate weather phenomenon that has its own size, seasonal cycle, and influence on the global climate. Each of these massive cyclones sits over the pole, spinning with the planet's rotation, with wind speeds that can reach up to 240 kilometers per hour. Why do these winds happen? The first piece of the puzzle is temperature difference. At locations like the equator, where sunlight is most concentrated, the air is warmed and starts to rise. As it does so, it creates an area of low pressure beneath it that draws air into it from its surroundings, like a giant vacuum cleaner. Meanwhile, at places like the poles, where it's much colder, air contracts and falls, creating zones of high pressure, where air molecules want to spread out like a crowd of school children being released into an open field. So, naturally, with these two forces at play, there is a tendency for air to rush from the poles towards the equator. Freezing cold winds are constantly trying to escape from the north and south poles. This model is a little simplified though, as wind does not travel in one continuous line from the pole to the equator. Instead, because air from the equator cools and falls much sooner than the pole at around latitude 30 degrees, and air from the poles warms and rises much sooner than the equator at latitude 60 degrees, there are three cells of air on each hemisphere that air circulates in: the polar cells, the air masses above the poles, and the Hadley cells, the air masses above the equator. Both cycle in the temperature-driven way I described. However, the middle cell, known as the ferrule cell, is not temperature-driven. Like a gear, it is dragged by the rotation of the other two cells and rotates opposite to their motion. In terms of our northern polar vortex, this means that once the air from the pole heads south, it's met by warmer wind traveling in the opposite direction. And when two air fronts of different temperatures meet, they clash rather than mix. So the polar vortex is trapped, bounded, clashing against winds coming in from all sides. There's more at play here though. If this was on its own, the cold air from the north would just slide underneath the warm air from the south, not really being trapped at all. There is a second force at play that redirects those winds spinning them into a vortex that keeps them circling the poles rather than coming down towards the equator. Where does this spin come from? It's due to something known as the Coriolis force. In a simple, flat world, cold wind from the poles would travel towards the equator, while warm wind from the equator would float over it towards the poles. But the world isn't a simple flat sheet. It's a rotating sphere. You are traveling right now at somewhere between 0 kilometers per hour, if you're at the pole and decided to watch an Astrum video while you're there, and 1,600 kilometers per hour at the equator, from the west to the east. You might not notice this fact because everything next to you is, on average, traveling at the same speed in the same direction. But what happens if you were to travel from the equator to the pole? Conservation of momentum states that you would still be traveling eastward at the same speed as previously, but suddenly the Earth beneath you is not traveling quite so fast. Remember, at the pole you'd have 0 eastward speed, but would simply be rotated slowly. If, on the other hand, you keep all your eastward momentum from the equator and travel towards the pole, suddenly it will appear, compared to everything else, like you are traveling east really fast. In practice, this means that air that travels up towards a pole from the equator, whether towards the North Pole or the South, will not go straight up, but over large distances will start to curve towards the east. This rapidly eastward traveling air is why you get jet streams. There are at least 4 of these, straddling the gaps between the Hadley cells, the Ferrel cells, and the polar cells. The subtropical jet stream lies between the first 2 and is a little weaker, but the jet streams we are interested in are the polar jet streams, wringing the frigid air off that develops in the North and South poles. These ribbons of air circle the globe in an almost continuous path, a little underneath the boundary between the troposphere and the stratosphere. They are only a few kilometers deep, but can be hundreds of kilometers wide, and in their hearts, the wind can travel at 400 kilometers per hour. As a reminder, over 120 kilometers per hour is getting into strength level of hurricanes.
Damn.
The jet stream around the South Pole is fairly stable. Its powerful winds overrule the polar winds trying to leave the polar air mass, whipping them along with it and dragging the entire polar cell into a massive Antarctica-spanning vortex. At this point, a keen-eyed observer might have noticed a flaw in this model. If conservation of momentum means that air going from the equator towards the pole veers towards the east, why is it that air traveling from the pole towards the equator doesn't do the exact opposite? It has 0 momentum, moving to zones that have considerably more momentum. Comparatively, it should be quickly left behind, appearing to start spinning to the west. This is true, but cold winds have much more friction to contend with as it starts to slide underneath the warm front and then drags along the ground. This seems to slow it down enough that the countervailing jet stream overrules it. It's important to note this tension at play though, as it becomes much more important.
Is that a
in the
real thing
polar
or that's
night
one of
jet.
the AI stuff?
The polar night jet is the jet stream that bounds the vortex at the North Pole. Specifically, it bounds the stratospheric polar vortex, keeping it in check during the coldest part of the year for the North, the polar night. Here, during the winter months, the sun is absent from the sky entirely, creating even more freezing temperatures. Interestingly, this colder climate creates a deeper pressure difference between the air around the pole and the air further south, which actually strengthens the force that creates the polar night jet, meaning that during the coldest part of the year, this freezing air is usually well contained. However, this does not always hold true. There are things that can disrupt a jet stream. There are certain zones, such as the boundary between sea and land, or the presence of a large mountain, that can cause disruption to wind. Coastal environments create their own winds that can suck in jet streams, while mountains force an air current to move around it. Even other weather phenomena, such as El Niño, which you might recognize from one of my recent videos, can have an impact on the path the jet stream takes. As the jet stream is not fixed down, but is a balancing point between a range of opposing forces, hitting such obstacles causes it to deviate from its course, and once it starts deviating, it will rock back and forth like a string that has begun bouncing. It shifts, no longer in its balance, overcorrects itself, and is no longer in balance again, and overcorrects itself again, in massive planetary waves that cause the polar night jet to meander around the Earth rather than travel in a straight line, and these oscillations can reach a point where there is a breach. The first sign of this comes in the form of a sudden stratospheric warming, most common in late winter. An SSW can even represent a time where temperatures rise in the polar region by as much as 50 degrees Celsius over the course of just a few days. Something within the system of the jet stream can be so thrown by this that it leads to the southern moving westerly winds overpowering the jet stream, partially or completely reversing its flow. No longer contained, Arctic wind moves south and meets warmer and warmer air, and pushes faster and faster south in an attempt to balance the gradient. The entire jet stream buckles, and suddenly it pivots. It massively reorients itself, traveling down the planet so that regions like Europe and America, usually safely on the warm, temperate side of the polar night jet, suddenly find themselves in the domain of the polar vortex. The forces of winter have arrived. In fairness, not all of these events are devastating. With sufficient preparation, you can simply put on some warm clothes, or try to avoid going outside for the month or so that the polar winds are overhead. As long as you're ready for cold, it's not the end of the world. However, sometimes the outcome is serious. In the UK, in 2009 to 2010, the Big Freeze saw parts of Scotland reaching temperatures as low as minus 22 degrees Celsius,
winter was already
the
in
coldest
Ireland.
in nearly 40 years,
It was freezing
with
temperatures here.
widespread transport
and-
disruption,
yeah.
event closures and power failures. Sadly, this in turn led to the death of 25 people. In the US, the 2019 January-February North American cold wave saw a polar vortex move down across much of the country with similar outcomes. Some areas saw temperatures as low as minus 50 degrees Celsius if you take into account wind chill factor from the blustery freezing winds. Snowstorms raged. You could get
Crazy.
frostbite from being outside in just 10 minutes. Sadly, another 22 people died, with hundreds more needing frostbite treatment. Responsible was the ranging polar vortex. In time, the imbalances in the global temperatures restore themselves, and the jet stream returns to its previous position. However, it's worth noting that some level of jet stream breakdown occurs in the north 6 times every decade. If you live in the northern hemisphere, you will likely see many more of these events over the course of your lifetime, although hopefully not all as powerful as these 2 examples. In the south, you are likely safer. There have only ever been 2 instances in recorded history of the solar polar jet stream breaking down in the same way as the northern one. It has happened though, and the mechanisms behind it are not fully understood. It's difficult to say, as global temperatures gradually rise, what influence this might have on the jet streams. Some evidence indicates that they are traveling further poleward on average year on year, although this is apparently not unheard of in the planet's history. There is some more evidence that the jet streams have strengthened since 2002. If so, we should be grateful. Although unpleasant, the biting cold of the polar vortex usually is only a passing weather phenomenon. We see it return north within a month, but if the jet stream were to go, the polar vortex would come down from the north to stay, and we truly know what it is like to live in Arctic conditions. The more I've learned about this subject, the more I've discovered that the winds of our planet are this fascinating weave of interplaying forces and effects that tug and pull on each other, finding perfect balances, and yet constantly shifting in rhythms and patterns. And yet, it does so practically invisibly. So much is going on that we simply do not see down here on the ground, just because air is, well, air. And yet, I've learned its importance. The polar night jet is not just wind with a cool name. It is a bastion of protection, a wall against the frozen wind. It really makes you think of the incredible majesty of the world around us, how much is going on that protects us that we simply do not see.
That was cool.
If you've enjoyed learning about the jet stream and the polar vortex, don't worry, there's more to discover. Jet streams as a phenomenon were not always understood, and there's an excellent article on them called Searching for the River of Wind on the website of today's sponsor, Nautilus. Nautilus is a fantastic science publication that I've become really impressed with lately for its accessibility, strong narrative sense, and fascinating insights. Its award-winning authors are scientists from many different disciplines, so you get cutting-edge research on all sorts of topics, including one near to the heart of any Astron viewer, space. Don't just take my word for it though.
Cool.
In a rare event, Nautilus is offering a 15% discount on their yearly membership, so now's the perfect time to go see for yourself. Check my link in the description below.
Huh.
Thanks for watching. If you like this video,
What happened there?
you'll love these other videos on the various cycles of Earth. A big
Okay. So, what do you think? Have you been a victim of a polar vortex in past decade or two? I remember in 2010, the winter of 2009-2010, it was very severe here. It was my second winter. Was it second? No, it wasn't second. It was like another winter. But basically, coming from Poland, I did grow up with winters that we, like the cold. There's snow, there's freezing temperatures and stuff, so we kind of got used to it. But then Ireland is different, especially the place where I live. It's more, it's warmer. And that winter back then, it was pretty terrible. The pipes and stuff froze, so there was no water. There were water shortages because people were buying off water from the supermarkets, and they couldn't, because of the bad, terrible road conditions, they were not able to actually deliver more and things like that. So it was quite terrible. Not as much as, let's say, what was happening recently in America with the polar vortex as well. And nothing like in Scotland as well, but still bad. People are not ready for stuff like that. When you're not ready, you're just not ready. That's what it is. Okay, thank you very much for watching, and I'll see you tomorrow. Bye!